Good afternoon, everyone. My name is McKim, and I'm a second-year physics major here at UCSB. This summer, I've been working with my mentor and PI, Dr. Leib Washburn in the Marine Science Institute. And today, I'm going to talk about how winds and sea level differences control coastal ocean currents. So, the coast of California is characterized by an upwelling circulation pattern, as shown in the diagram, where equatorward winds that are going to the equator, drive surface waters to move off the coast, and this brings cold, nutrient-rich, deep water up to the surface. It's this process that leads to the productive ecosystems we see along our coast, and it's all driven by the wind and the rotation of our Earth. So the region I'm studying is centered at Point Conception, a major biogeographic boundary. Points in red are oceanographic moorings which collect data on the ocean, and points in white are just locations. So to the north, along the central California coast, upwelling occurs, but stops at Point Conception because the abrupt change in coastline is no longer conducive to the process. This means that waters in the Santa Barbara Channel are much warmer and contain more tropical species than the cooler upwelled waters to the north. This means that a large range of species settle at Point Conception, such as the giant kelp forests pictured in the background. Ecologists working in this area need to have an understanding of the diverse flow phenomenon which occur because of their ability to bring in larvae, nutrients, or even pollutants from surrounding areas. So we want to get an idea of what the currents normally look like in this area, and they're all driven by the wind. So first, I'll note that we have these strong equatorward winds blowing for most of the year. But during the summer, we see that the winds die down over a period of about a couple days, and this process repeats about every 2 weeks, where the winds relax and disappear for a few days. And when this happens, we see the shift from when the winds are normally blowing, we see predominantly equatorward currents, to when there's no wind, a complete reversal of the currents in the area, where they originate in the Santa Barbara Channel and move poleward around Point Conception. And it's not intuitive why this occurs at first glance. So looking at these poleward flow events, we want to know, how do we even know these events are occurring? We want to know what physical processes drive them, and along the way, we'll take a look at the physical characteristics of these flows, such as the temperature and velocity, and relate it to the structure of these flows to figure out what they look like. So first we'll focus on how these flows are set up. When the wind is blowing strongly, we see a region of a sea level difference develop, where a region of high sea level develops in the Santa Barbara Channel, where the H is, and a region of low sea level develop north of Point Conception, where the L is. Now, let's take a look at this a little bit further. Here are two graphs superimposed on each other and plotted against time. In blue is the wind stress, which is a measure of how much force the wind puts on the ocean per square meter, where positive values indicate poleward winds and negative values correspond with equatorward winds. In green is a graph of the sea level difference between Alegria and Sal. Alegria is located in the Santa Barbara Channel and is higher than Sal, which is located in the north. So a positive sea level difference means that Alegria is higher than Sal. So we see that these two graphs are anti-correlated with each other. And when there's a big wind stress, we see a big sea level difference. And this relationship is shown by these red arrows. But when the wind relaxes, we see in the circled areas, when the wind drops to zero, we see the sea level difference in fact even reverse. And these sea level differences are on the order of 1 to 2 centimeters. So let's build a physical picture for what's going on here. The equatorward wind stress causes waters to pile up in the Santa Barbara Channel. And it's this piling up of waters which creates the difference in sea level. So this region of high sea level develops in the Santa Barbara Channel. But when the winds relax and disappear, there's nothing left to maintain the sea level difference. And thus, it'll attempt to go back to equilibrium where the two heights are the same. And this is what drives these poleward flows. So to get measurements on these poleward flows, we used what's called oceanographic moorings. And first thing I'll point out about these is the acoustic Doppler current profiler, or ADCP, which is located on the seafloor. ADCPs can measure both pressure and velocity, and it can measure velocity at different depths in the water column, as well as the thermistor, which is located on the mooring line. And these can be used to obtain a temperature profile of the water column as well. By knowing the pressure, we can calculate pressure gradients, or how the pressure is changing from point to point, and thus calculate the sea level difference between those points. By knowing the velocity, we can, at different places and different times, we can calculate the acceleration of these currents. And by knowing the temperature, we can calculate the density of the currents that we're seeing. So now we want to try to identify a useful marker for identifying these poleward flows. And since these processes are driven by the wind, it's useful to take a look at the wind stress, as this is what's really driving this circulation. So here's a graph of the wind stress. In an example on June 2012, it's a 10-day period. These two graphs, the magenta and cyan lines, simply represent two different locations the wind stress is being measured. So we see that the winds are strongly equatorward, but we're just going to focus on the time when the wind relaxation occurs, around June 10th, where the solid black vertical line is. Now, we know that there's a wind relaxation taking place. We'll take a corresponding graph during the same time and take a look at what the temperature of the water is doing. Now, the red line represents near surface temperatures, and the blue line represents near bottom temperatures. So we can see that there is a temperature spike on June 11th at all depths. And you may wonder why there's about a day-long delay between the wind relaxation and the arrival of the event at the Parissima mooring, which is north of Point Conception. And it's important to remember that these events originate in the Santa Barbara Channel and take about a day to travel up around the coastline. So we see that the temperature spikes by 4 degrees Celsius in just a couple hours. And this is a change that you can feel if you were in the water at that time. An important thing to notice about this graph is that both the bottom and the top temperatures of the water column are increasing at the same time, and nearly the same time, which suggests a vertical front associated with these flows. If we take a look at the along-shore velocities, so velocities parallel to shore, we can see that there's also a along-shore spike in velocity at the same time. And this spike lasts for about a day. The length of this spike tells us how long these flows are, how long these currents are. And it turns out these currents are about 17 kilometers in the head region, and I'll talk more about that later. You also note that the surface velocity is much greater than the sea floor velocity, and that's probably due to the interaction with the sea floor, which involves friction to slow down the water there. And now we'll take a look at the cross-shore velocities, where positive values correspond with towards the shore, and negative values correspond with offshore. And we see this classic upwelling circulation pattern once again, where surface waters are moving away from shore, and water depth is moving towards shore. But after the event arrives, there's a complete reversal of the circulation, where we now see surface waters moving towards the shore, and water depth moving away from shore. So now, another measure we wanted to see, physical characteristic, was if there is a sea level change associated with the arrival of these flows. This is a graph of the local sea level change at the Parissima mooring, the variations with respect to the average sea level. And we concluded that there was no significant change of the sea level during an event where the dashed vertical line is. But this may not be the case farther offshore. That'll be the subject of future investigation. So, using these physical characteristics of the flow, we can now build a picture for what these currents look like. And so here is an aerial view of what these currents look like. And we can see that we can divide this into two main regions, where we have a head region and a tail region. First, in the head region, this is what produces the spikes in a longshore velocity of about 0.4 meters per second we saw earlier. And it's with this that we have the alongshore scale of. Now, surface currents moving onshore is represented by the curved black arrow, and water moving away from shore is represented by the dashed arrow. And now looking at the tail region, we can further split this up into two areas where closer to shore, the velocity after the head of the current arrives is actually 0. But farther offshore, that's the region that supplies water to the head of the current. And measurements of Q, which is the volume transport of water, is obtained by high-frequency radar systems. And it's these systems that tell us that the width of these currents is about 10 to 20 kilometers. It's not too well defined. And looking at a cross-section of these currents now, we can see ahead of the current, up here, is the cold upwell waters with surface waters moving offshore and water depth moving onshore, and how it's completely reversed in this case after the current has arrived. So these pictures are important because they give a visual representation of the spatial and temporal scales of these currents, and this will help us understand their role in larval delivery across biogeographic boundaries. So in the future, studies will focus on the dynamics farther offshore, where, as you can see, we're not too sure of what the outer regions look like. It's not as clearly defined. And to our right, we see pictures of mussels at Lompoc Landing, which is north of Point Conception. These have already shown to be impacted by poleward currents. And future investigations will look at the changes in larval delivery, pH, and dissolved oxygen content levels associated with these flows. And with that, I'd like to thank the NSF, the SBC, LTR, and CSEP's EUREKA program funding me this summer, as well as my mentor, Lev Washburn, Chris Gottschalk, and Carter Ullman for their guidance. So thank you. Any questions? Yeah.
In one of your graphs, when you were saying, I think it was the temperature one, how you're saying that when the surface and bottom rise at the same time, it means it's a vertical track?
Yeah.
If they're not rising at the same time, what does that mean about the structure?
It means, so if you look at this diagram here, you can see that it's curved slightly, but it's mostly vertical. If we saw a big gap between the top rising first and the bottom rising well afterwards, we would have expected a much more slanted front. So this line would have been much more slanted. That's what I meant, yeah. Yes?
So I noticed why your data was from 2012, but is there recent data
Yes.
that are occurring? Or?
This was just a particularly strong event that occurred in 2012. We have more recent data that's been taken continuously since 2000. And in fact, when looking at more general characteristics of these flows, we tend to create ensemble averages of these. So we look at multiple different events. This is just one specific example. But these happen, like I said, about every 2 weeks during the summer. And this is just a particularly strong example. Yes.
Follow up on that question, what was happening like atmospheric-wise that allowed for the 2012 June month to be so much more relaxed than typical winds?
I'm not sure too much about what makes an event particularly strong, but these wind relaxations have been associated very recently with larger scale atmospheric variations, and I don't know too much about that, but we do take a look at what the atmospheric pressure variations are during an event, but I'm not sure about the magnitude.
Thank you. Should we have time for one more question?
Hey.
Okay. What kinds of fluctuations or errors in measurement do you have?
I got the pressure measurements at one point, and those show really big variations due to tides. The variations at sea level we were trying to detect were about 10 centimeters, but the variations in tides cause about variations the size of this room, and it's periodic motion, so we can subtract that data out with a harmonic fit of the data. But that's usually the biggest variable that we have to account for.
Thank you.